Welcome to Lesson 3, Security Engineering, End of Lesson Exam Review. So in the second half of Lesson 3, we talked about cryptographic processes, including a bit of a history of cryptography. We looked at the various types of ciphers and techniques. We talked in depth about encryption, both symmetric encryption and asymmetric encryption, and the use of public and private keys as well as session keys. We then delved into PKI, including the use of digital certificates, how we get a certificate, and the types of certificate. We then looked at hashing, creating a one-way representation of data to ensure integrity. We looked at message digests. We looked at the use of digital signatures. We then turned our attention to common cryptographic protocols and how they incorporated encryption and hashing and digital signatures to ensure confidentiality and integrity and non-repudiation. We took a look at some of the more common cryptographic attacks, and then we switched gears out of cryptography and we started looking at physical security. And first we looked at site and facility design principles, and then we looked at securing facilities, equipment, and people. So those are all of the areas that we covered in the second half of Lesson 3. So we're once again going to go through some questions to both sort of test your knowledge as to what you remembered, but as importantly, to talk about how you should approach your test questions. So here's our first one. Allison and Bob want to securely communicate. The mechanism they should choose is blank. If Alice wants to send Bob a secure message, then she needs his blank key. So I would start this question with just trying to fill in the blanks without even looking at the answer, so that I'm not going to get confused by what the answers are. Now, if it turns out that the answers I put in are not in the list, well, I'm going to have to revisit. Or if I'm not quite sure, sometimes I'll look at the list of questions to give me a hint. But let's start with sort of thinking about how you would answer this question before you even saw the multiple choice answers. We say that they want to securely communicate. The mechanism they should choose is, well, we said when we wanted to securely communicate, which really infers confidentiality, confidentiality is going to mean encryption. So more likely than not, the answer is the mechanism they should choose is encryption. So if Alice wants to send Bob a secure message, then she needs his key, some kind of key, and they're telling us it's his key. So what would she need? Well, she certainly wouldn't have his private key because Bob has to keep his private key secure. So she would need his public key. Remember, if she secures, in this case we'll know it's going to be the session key, but if she secures by encrypting plain text or the key value with Bob's public key, only Bob should be able to open it up with his private key. So if I was looking at this, I would say the answers would be encryption and his public key. Let's see what options we get. Well, the first one is encryption, and we like that. But then it says if Allison wants to send Bob a secure message, she needs his session key. Session key is symmetric, so it wouldn't belong to Bob. So we're going to get rid of that. The second one is the mechanism they should choose is digital signatures. Digital signatures does not give us confidentiality. Digital signatures by themselves are going to give us integrity and non-repudiation. So right away, we're going to get rid of that one. And of course, she wouldn't have Bob's private key, so we can take that away. The mechanism that she should choose is hashing. Hashing isn't going to give us any type of confidentiality. Hashing is just going to give us integrity. And assault, well, assault isn't a key, so we're going to get rid of that one. So how about this last answer? The mechanism they should choose is encryption, or encryption implies confidentiality. And if Alice wants to send Bob a secure message, then she needs his public key. So that's the answer we like. Again, I would start this question by trying to fill in the blanks before I even look at the answers. If I wasn't quite sure, I'd see if I could get some hints. But even if I had the answer on the very first one, even if A was encryption in public, I want you to make sure that you read all of your choices in case something changes by the time you get to your last choice. Question 2. Alice and Bob want to make sure that their messages cannot be modified in transit and wants to ensure non-repudiation. They should use, well, let's go through this again. We want to make sure that they're not modified in transit. That's telling us that they want to ensure the integrity of the message. And they want to ensure non-repudiation, meaning that the sender can't say, it didn't come from me. Well, if you read this question even before you get to the answer, you should know that we want a hash value, a message digest. That will tell us about modified in transit. And non-repudiation is going to be the digital signature. And the digital signature, of course, also includes the message digest. So hopefully you thought, they should use digital signatures. So let's see what comes up. Hash message digest. Well, yeah, they do need some hashes, but let's keep going through our answers. A digital signature, well, we like that one. That's the one we thought it was going to be. Digital certificates, well, you know, they do need to have public and private keys. They need to understand this, but that in itself is not what's going to ensure that their message can't be modified in transit or ensure non-repudiation. And they don't need encryption because they're not looking for the confidentiality. So while the hash message digest is going to ensure the message in transit, it doesn't ensure non-repudiation. So that brings us right back to the answer we thought it was, which was digital signatures. Let's go to question 3. A blank attack tries all keys until the correct key is identified, and the attack is only limited by blank and blank. That's a lot to fill in. So you may try to do this again before you even look at your answers. See if you know it intuitively. And if not, let's start looking down through the answers and see what makes sense. Our first option is a birthday attack tries all keys until a correct key is identified. The attack is only limited by time and key space. When we know a birthday attack is based on the probability that if you have 23 or more people, there's a 50% probability that they'll have the same birthday. But that would be a collision attack. So if we said a collision attack tries all keys until the correct key is identified, that wouldn't even make any sense because that's going to be a hash attack. So we're going to get rid of that one. If we go to B, we've already determined that a birthday attack is a collision attack. So if we try to fill in the sentence with this one, a collision attack tries all keys until the correct key is identified, and the attack is only limited by the algorithm and key security. Well, again, the algorithm and key security doesn't really relate back to the issues with collisions. Let's try C. A brute force attack tries all keys until the correct key is identified. Remember, a brute force attack says I'm going to just keep trying and trying and trying and trying. We'll see brute force attacks in other areas besides cryptography. We'll see brute force passwords attack. We keep trying to get the password, keep trying it, keep trying it. So a brute force attack means over and over again. And the attack is only limited by time and resources, resources being processing power. So far, we like that one best. A man-in-the-middle attack tries all keys until the correct key is identified. The attack is only limited by personnel and money. Well, none of those answers really fit. A man-in-the-middle attack is going to try to capture the transmission, make some changes, and then send it on its way. So it has nothing to do with the keys. It really has little to do with personnel and little to do with money. So we don't like any of those options. So C, which we liked best to begin with, a brute force attack tries all keys until the correct key is identified. The attack is only limited by time and resources. Question 4. HTTPS is a combination of what protocols? Now this is an example of an answer you're just going to have to know. Because our choices are HTTP for all of them, A, B, C, and D. And then we've got 3 choices. It's a combination of SSL, Secure Socket Layer. It's a combination with SSH, Secure Shell. A combination with IPsec, or a combination with SMIME. Now, if you're really stuck, you might say, well, I'm going to look for the S, but that doesn't really help you too much. We've got an S in SSL, an S in SSH, and an S in SMIME. So it's important that you be able to recognize the protocols and recognize all of the terms that we've been talking about through this course. That HTTPS is a combination of HTTP and SSL. And lastly, we're going to go to question 5, which is not, and not being an important word here, which is not a physical security engineering principle. And our options are going to be obstacles, detective controls, septhead, and response mechanisms. So which of these is not a security engineering principle? Well, we talked about the 3 principles, and then we talked about a design consideration. Remember, septhead, crime prevention through environmental design is a design principle. It's not a physical security engineering principle. As a matter of fact, it's really an emerging area of architecture. So that's not going to be your security engineering principles. The ones we talked about were obstacles, because obstacles will frustrate trivial attackers and slow down determined ones. Detective controls is a physical security principle because that lets us know that an attack has happened or is happening. And response mechanism is a physical security control because that's how we're going to respond to a physical security attack, which leaves CISSP, which is an architectural design principle, not a physical security engineering principle. If you really were struggling with this, the way to approach it is knowing that obstacles, the detective controls, and the response mechanisms kind of all go together, which was going to make the CISSP the odd man out. Which one is not like the others? So now when we look back at all of Lesson 3, you can see what just an immense lesson this was, starting with secure design principles, through security models, selecting controls, our information system capabilities, our security architecture vulnerabilities, our cloud vulnerabilities, our web vulnerabilities, our mobile and remote computing vulnerabilities, and then going into the cryptographic processes, encryption, PKI, hashing, digital signatures, cryptographic protocols, cryptographic attacks, site and facility design, and securing facilities, equipment, and people. Again, this is a very, very large domain. As you're studying, you may want to take it in chunks. There are some areas that seem to go very well together. In the first section of secure design principles, really through selecting controls. Then we have all of the areas of vulnerabilities. Then we move into cryptography. And then the fourth real area is in physical controls. If you feel like you're not strong yet in any of these areas, I would encourage you to go back to the appropriate lesson and go through it again. Keep going through these lessons until you feel really confident. One of the things that's so unique about this exam is how broad it is. So it's really important that you're comfortable with a broad spectrum of information. Thank you for joining me for this domain, and I look forward to seeing you in the next lesson.